Now that we've covered implicit differentiation, we're now able to differentiate inverse functions. Let's begin with an example. At first sight, finding the derivative of the inverse sine of x seems impossible. But let's try the trick of implicit differentiation again. So what I'm going to do is let y equal the inverse sine of x, so that implies that the sine of y is just x. Now I'm going to differentiate both sides with respect to x, as we did before. So the derivative of inverse sine of x is 1 over cos y. Now what is that? Using the identity cos squared plus sine squared is equal to 1, I can write cos y as the square root of 1 minus sine squared x. So that means using this trig identity, I can rewrite the cosine in terms of sine and then resubstitute for y in terms of x. And that tells me that the derivative of the inverse sine of x is 1 over the square root of 1 minus x squared, provided of course that x is between minus 1 and 1. So really the trick here was to use implicit differentiation. But let's have a look at what's actually happened. If I have a general inverse function of x, then I let y equal inverse function of x. That means I can write that f of y is equal to x and then differentiate implicitly. So that implies that f prime of y times dy by dx is equal to 1. And again, the prime on the f is the derivative with respect to the argument y and not with respect to x. So this implies then, if I rearrange dy by dx is 1 over f prime of y, and this is equal to the derivative of f prime inverse of x. So that's a general formula to find the derivative of an inverse function, which you can use if you like. But I think it's easier just to always use the same procedure and use implicit differentiation. Let's do a couple more examples. Let's find the derivative of the inverse cotangent of x. So first we start with y is the inverse cotangent of x, which means that x is the cotangent of y. And this implies that 1 is equal to x tan y. Now I differentiate with respect to x. So on the left we get 0, and on the right we have a product, so that's tan y plus x times the derivative of tan, which we've shown before is sec squared, times dy by dx. So now we rearrange for dy by dx, which is minus tan y over x sec squared y, and this simplifies to minus 1 over x sine y cos y. Now, that's not a very satisfactory way to write out the answer, so let's convert the y into x. Now, to do this, I'm going to use an auxiliary triangle. This is a nice way to convert one trig function into another. So I let y be the angle, and I know that tan y is equal to 1 over x. Tan y is 1 over x, which means on my triangle, I can write opposite is 1, the adjacent is x, and so the hypotenuse is 1 plus x squared, and so I can now read off what sine y and cos y must be, and this gives me my final answer, d by dx cot minus 1x, which is minus 1 over 1 plus x squared. And you can do the same procedure for all the other inverse trig functions. What about inverse hyperbolic functions? Well, again, the same thing works. Let's just go through an example. Let's find the derivative of the inverse cosh function. Now we differentiate both sides. So therefore, dy by dx is 1 over sine y, leaves me the derivative of the inverse cosh is 1 over the square root of x squared minus 1.